Okay, so this will be the last lecture over this chapter. So this lecture will look at the half-life of nuclear reactions and then look at a few applications of nuclear reactions. Okay, so half-life is something that we've talked about before back in the kinetics chapter. So half-life is the time it takes for 1/2 of a radioactive nuclei to decay, or how long it takes for half of a sample to decay. So the rate of radioactive decay of an unstable nucleus is a constant. So it depends only on the nucleus. Doesn't depend on the temperature, doesn't depend on the pressure, doesn't depend on the concentration, how much of the nuclei there is. Obviously, how much radiation will come out depends on how much radioactive nuclei there is, but how fast that process takes does not depend on how much there is. Right? The rate only depends on what the specific nucleus is that's decaying. So different radioactive nuclei have different decay times. So iodine 131, for example, has a half-life of 8.07 days. So something like this might be something that's useful in medicine. You know, if you're going to have a radioactive nucleus used in medicine, obviously you don't want it sticking around for a long time. So the faster it decomposes, the better, but it can't decompose too fast because it's still got to have a long enough lifetime to be useful. And then ideally you want something that the body can eventually eliminate as well. So some radioactive elements have extremely fast half-lives, microseconds or faster than that. Some, relatively long lifetimes like 8.07 days, or some have an extremely long lifetime like uranium-238, which has a half-life of 4.51 billion years. Okay, so there's two main equations when we're dealing with half-lives that you'll have to know how to use. So half-life is equal to 0.693 over K. So this is the equation you saw before back in the kinetics chapters. So radioactive decay is a first-order process, so that's an equation for a first-order reaction where K is the rate constant for that process. And ln of nt over n0, so nt is the amount of radioactive material after some time t, and n naught is the amount of radioactive material at start that you start with. So that ratio is equal to negative KT. So K is the rate constant and T is the time. So let's take a couple of problems just to illustrate. So the rate decay for technetium-99 is 1.0 times 10 to the minus 13 seconds, so that is a rate constant K. So what is T1/2? So a pretty easy calculation, you just need this equation. T1/2 0.693 over K. So just plug in 0.693, plug in your rate constant. And solve, and you get 6.9 times 10 to the 12 seconds, or 2.2 times 10 to the 5 years would be its half-life. Okay, so phosphorus 32 has a half-life of 14.3 days, so what fraction remains of phosphorus 32 from a 0.28 gram sample after 5.5 days? And so how many grams would actually then still be present after 5.5 days? So to solve this, we need a couple of equations. So we need that equation, and T1/2 equals 0.693 over K. So you're not actually given K in this problem, but K is equal to 0.693 over half-life over T1/2. So we can take that and plug that in to this equation for K. So we are given T, right? T is 5.5 days, and we're given T1/2 is 14.3 days. Okay, so ln of nt over n naught will equal negative 0.267. And so if you remember how to do this mathematical manipulation to get rid of natural logarithm, so it'll take e to both sides. So nt over n naught will equal e to the negative 0.267, which is equal to 0.77. So the question just asks for the fraction. So the fraction is 0.77, so 77%. So 77% of the starting material remains after 5.5 days. So to calculate how many grams, then we just take the 0.28 grams times 0.77. So 0.21 gram remains after 5.5 days. And the other 0.07 gram has decomposed over that time. Okay, so after about 5 half-lives, about 3% radioactivity remains. That's easy to illustrate. So if you had 1 gram of iodine-131, for example, half-life of 8.07 days. So if you start with 1 gram after 1 half-life, you would have half a gram after 2 half-lives. In this case, since it's iodine, so after about 16 days, you would have 0.25 grams. After 3 half-lives, 0.125 grams. After 4 half-lives, so after about 32 days, you would have 0.06 grams. And after a 5th half-life, you would have 0.03125 grams, or 3.125%. So after about 5 half-lives, you're down to about 3% radioactivity remaining. And again, that can be really fast, or that can be a long time, depending on the half-life of the radioactive element. Okay, so lastly, look at a few applications of radioactivity. Also, one is in power. So nuclear power plants obviously utilize nuclear reactions. That's the source of power. So we'll go through how that works. So this is going to be on a large scale, like a nuclear power plant. Right? Texas has a nuclear power plant just southwest of Fort Worth. Or it can be on a small scale. It can be used to power satellites, power pacemakers, things like that. Radioactivity is used in smoke detectors. This is how smoke alarms can work. They have an ionization chamber that it conducts electricity, because as we saw in the previous lecture, when radioactive alpha particles, beta particles come into a chamber, can ionize a gas, and then that can complete a circuit to give a electrical signal. And so a smoke detector can have that as part of the smoke detector, but then when smoke comes in to the ionization chamber, it can block that process, and that would disrupt the electrical signal, and then that would be when the smoke alarm goes off. We saw some examples of how it's used in medicine with PET scans or imaging agents like technetium. So we'll look at a couple more examples. So radioactive dating, nuclear weapons, how do they work? So for radioactive dating, so carbon, so comes as 3 isotopes in nature. We have carbon-12 and carbon-13 with 6 protons and 6 neutrons, or 6 protons, 7 neutrons. Those are stable. Carbon-14 Right now, your ratio of neutrons to protons getting a little bit too big, and so that's not stable. And it's going to undergo beta decay, right? You got 8 protons, 6 neutrons, so that ratio is a little bit more than the 1.0 to 1.1 for a small light element. So it's going to undergo beta decay, and so carbon-14 is an unstable nucleus, radioactive. It'll be converted over time to nitrogen-14 plus a beta particle emission. Okay, so half-life of carbon-14 is 5,730 years. So obviously you couldn't use it to date something that's really, really old, because after 5 half-lives, so after 5 times 5, 25, 30,000 years, there's not much carbon-14 left. But it can be used to date something that's not that old. So how does this work? So where do you find carbon in nature? Well, one place you find carbon in nature is CO2. So most of the CO2 in nature has carbon-12 in it, because carbon-12 is about 98.8% natural abundance. But some of the carbon, and then there's about 1.1% natural abundance carbon-13. But there is some carbon-14 in nature, trace amounts. And so, how does a plant use CO2, for example? So, oops. So plants use CO2, right? So if you have some carbon-14 CO2, and a plant can take that up through photosynthesis. And then what happens to the plant? Well, eventually the plant would die. And so now it's no longer doing photosynthesis. So now there's no uptake of carbon-14. So as long as the plant is alive, then it has a pretty constant amount of carbon-14 in it. But then once it dies, then it's no longer taking up carbon-14. And so the carbon-14 that is in the plant now is going to be decaying, so the amount of carbon-14 decreases. So if you simply have an artifact fossil and measure the amount of carbon-14 in it, then based on how much radioactivity you get, you can date how old that artifact is. Same would be true for an animal, because an animal eat the plant, or the animal would eat something that ate the plant. So the animals would have carbon-14 in them as well. So as long as they're alive, they have a pretty constant amount of carbon-14. Once they die, then the carbon-14 is no longer being uptaken. So the amount of carbon-14 would eventually decrease, and then you could use how much is remaining after a specific amount of time. Since you know the half-life, you can figure out how old that artifact is. Okay, nuclear weapons. Obviously one of the not so nice areas of nuclear chemistry. So, how does a nuclear weapon work? Well, so if we take something that's radioactive, like uranium-238, for example, it's got a mass of 238.003 AMU, or grams per mole, and it undergoes nuclear decay to thorium-234 and alpha particle. So these have mass of 233.9942 and 4.001.50. So if you add up the masses, so take the masses of the products. So if you add the thorium and helium together and subtract off the mass of the uranium, then there's a mass difference of 0.0046 grams. So where did that, so 1 mole of uranium-238 decompose into thorium-234 and helium and an alpha particle, where did that mass go? Well, that mass is converted into energy, so E equals mc squared. So if we do the calculation, so if we put in the mass difference, convert grams to kilograms, multiply by the speed of light squared, then you get 4.13 times 10 to the 13, or 4.13 times 10 to the 11 joules of energy. That would also come out of this reaction. So that would be exothermic by 4.13 times 10 to the 11 joules per mole of uranium-238. So that's a lot of energy. So 1 ton of TNT, when it explodes, it would generate 4 times 10 to the 9 joules. So 20,000 tons of TNT would generate 8 times 10 to the 13 joules. So if we did this calculation for uranium-235 instead of uranium-238, so 1 mole of uranium-235 would generate 4.13 times 10 to the 13 joules of energy. So that's the equivalent of about 20,000 tons of TNT. So 1 ton, of course, is 2,000 pounds. So 1 mole of uranium-235 is only 0.518 pounds. So 0.518 pounds of uranium-235 would produce 4.13 times 10 to the 13 joules of energy. Tremendous amount of energy, especially if it's released in a very short amount of time. So basically, how does that work? Well, if you have a uranium-235 atom, so if you bombard this with a neutron, then it'll undergo nuclear decay. So uranium-235, so that would make a uranium-236 atom, which then undergoes nuclear decay to a barium-141 plus a krypton-92 plus 3 neutrons plus a gamma ray plus energy. Because if you add up all of the masses on the products don't equal all of the masses of the reactants. So you have a mass difference, and if you calculate the mass difference, you get 4.13 times 10 to the 13 joules of energy would be produced in this reaction. Okay, so basically how this works. So what's significant to note is that every one of these that decays, 1 uranium gives off 3 neutrons. So if you bombard a uranium with a neutron, then it gives off 3 other neutrons. And if those hit a uranium-235, well, then that starts this reaction again. And so each of these then will give off more energy and 3 more neutrons. So you can see, so 1 uranium originally gave off 3 neutrons, and those 3 neutrons hits 3 more uraniums, and those give off 3 more neutrons. So now you have 9 neutrons, and if those hit 3 more uranium, or 9 more uraniums, then you give off 27 neutrons, and now you have what's called a chain reaction going on. And so this is just magnifying, right? One simple reaction becomes 3, which becomes 9s, which becomes 27. Tremendous amount of energy being given off each time, and that's basically how a nuclear weapon works. So a nuclear power plant works on a similar principle. It's just controlled. So you have a neutron, comes in, hits a uranium-235, which then gives off 3 other neutrons, just like in a nuclear weapon. But you have what are known as control rods set up in the nuclear power plant. And these control rods contain boron, because as we saw in previous lectures, boron absorbs neutrons. So you let one of them, for example, go on and hit another uranium-235, but you let 2 of them hit a control rod, so that you don't have an exponential amount of uraniums undergoing decay. You just have 1 uranium at a time, for example, undergoing decay. So in that way, you have a more controlled release of energy. It doesn't keep magnifying. You just get the same amount of energy coming out each time. So as long as the control rods work, then this reaction doesn't get out of control. So you use the energy that's that's produced to heat water, which of course is turned to steam, which is used to turn a turbine, and now you have electricity. So how are the boron control rods working? We looked at this in a previous lecture. Right, boron would absorb a neutron into its nucleus to make boron-11, which is then radioactive, and it decomposes to lithium-7 plus alpha particles. So you're still generating a lot of radioactivity in the process, but at least you're capturing neutrons. To prevent the escalation of the uranium-235 decay to get out of hand. And of course that can be what happens in a nuclear meltdown. Something goes wrong, control rods are not working, and too many uranium-235s start undergoing nuclear decay. Too much energy is produced too fast, then the core can melt down, and then you can have a nuclear explosion on your hands. So yeah, in that regard, nuclear power plants could be dangerous if something like that ever happens. Of course, obviously, it has happened before, but it's obviously a lot of control measures put in place to avoid something like that. So one of the problems with power plants, nuclear power plants, is other than the possible problem of a nuclear event, explosion happening at a power plant, and the other main problem is that they produce nuclear waste. And then how do you deal with the nuclear waste? Well, what the United States does is they basically just set on the nuclear waste. They basically have 3 or 4 main sites, and they just accumulate the nuclear waste there, bury it, and let it just decay over time. There are some countries like France who reprocesses the nuclear waste. Basically, they reuse it. Downside to that is that some of the products of the nuclear waste, one of the products is plutonium-239. And it can be weaponized. So there's a little bit, so obviously some controversy with reprocessing the nuclear waste as well, because if you concentrate and purify the plutonium-239, then that could potentially be funneled off into terroristic activities or something like that, because it can be weaponized. But other than that, nuclear power plant's extremely clean source of energy, so long as there's not any problems and you have an effective way to deal with the nuclear waste that comes out. Okay, so that's a few examples of using nuclear radioactivity for useful purposes.